the partial pressure of oxygen in the alveoli is not the same as the partial pressure of oxygen in the atmosphere. And that's for a variety of different reasons that we will take a look at. So, the first thing that we have to remember is that the partial pressure of oxygen in a dry mixture is equal to the atmospheric pressure times the fractional component or composition that is oxygen. So in atmospheric air at sea level, PO2 is equal to 760 millimeters of mercury times 0.21 because it makes up 21% of the atmospheric air, which is equivalent to 160 millimeters of mercury. So that is the partial pressure of oxygen in atmospheric air. Now, when we inhale air, one of the things that happens is that the air is humidified to saturation. We put water vapor into that air. Now, why would we want to do that? Because if we were to just inhale this dry air, what would happen is all of the surfaces lining our respiratory tract would dry out, right? They would take the water from lining our respiratory tract and it would pull it into the air. It would dry out our tissues, which would cause damage to our tissues. That's not good. So we actually humidify the air when it comes in. So we have to account for that. So if we sort of do so, our partial pressure of oxygen is equal to the pressure of the atmosphere minus the pressure of the water vapor after we humidify the air, then multiply it by the fractional component of the inspired air, that is oxygen. So if we sort of write this out, we do again. We've got our 760 millimeters of mercury of atmospheric air. We are going to subtract about 50 millimeters of mercury, which is saturation for a mammal, for water vapor at normal operating body temperatures. And then we're going to go ahead and we're going to multiply that again because the gas's composition of oxygen is 21%. So if we do all of that, that is going to give us 149 millimeters of mercury. So notice, right, just by humidifying the air, we've decreased the overall partial pressure of oxygen of that inspired air. Now, the other thing that we have to remember is that as the air enters the alveoli, gas exchange is happening across the alveolar surface, and our body is metabolizing the components, creating carbon dioxide, which is going to get put into that alveolar space. That carbon dioxide will get put into alveolar space, and we're going to consume that oxygen. So what we say is that the alveolar partial pressure of oxygen is actually equal to the partial pressure of the inspired oxygen, which was this, our 149 millimeters of mercury, minus whatever the O2 consumed is. And we can say that the O2 consumed is equal to the partial pressure of carbon dioxide in the arterioles divided by R, where R is the respiratory exchange ratio. So this is the exchange ratio, also known as the respiratory quotient and abbreviated RQ. So this is the exchange quotient. So basically what this is telling us is how much CO2 is being added into that alveolus and how much oxygen is sort of being taken out. So if we then account for all of that, right, that the exchange quotient for an average sort of mammal is 0.8, and a partial pressure of carbon dioxide of about 40 millimeters mercury. Let's go ahead and plug all that in now. So we have partial pressure of oxygen in the alveoli is equal to the atmospheric pressure minus the pressure of the water vapor, all of that times the fractional composition of the inspired air for oxygen. And then all of that minus the O2 consumed, which is the arterial carbon dioxide, over the exchange quotient. So then if we plug some numbers in, PaO2 is equal to 760 millimeters of mercury minus our 50 millimeters of mercury for our water vapor times our 21% that is oxygen minus the 40 millimeters of mercury for the partial pressure of carbon dioxide divided by 0.8 for the exchange quotient, which equals about 99 millimeters of mercury. So notice that we started all the way up here at 160 millimeters of mercury of partial pressure of our dry atmospheric air, and then we got to 99 millimeters of mercury by the time it was all said and done, and we're sitting inside of the alveolus. And so all of these things contribute to that overall partial pressure of oxygen. So then sit back and think about, okay, now if I were to do all of this again at Mount Everest, how would that compare, and what would your partial pressure of oxygen end up after all of this was said and done?